Hello everyone. In this module, we can discuss the probability of error for binary PSK system. So in the last module, we have calculated the probability of error for binary ASK. Almost all, let us follow the same procedure. First, let us start with the consideration, general consideration for probability of error expression for optimum filter. We calculated in the previous modules and we obtained it as probability of error for optimum filter as half ERFC of x01 of t minus x02 of t divided by sigma, where x01 of t minus x02 of t by sigma is nothing but our output SNR. Okay. First, let us, and we also defined, we also calculated the square of output SNR rho max in optimum filter as rho max is equal to x naught of t divided by sigma whole square, where x naught of t is the change in the output magnitude, which is expressed as x naught 1 of t minus x naught 2 of t. Here x naught of t is nothing but x naught 1 of t minus x naught 2 of t by sigma whole square, because you are defining square of output SNR. And for optimum filter, we derived it as integral minus infinite to plus infinite x of f square divided by SNI of f df, where x of f represents the change in the input magnitude in frequency domain. And similarly, SNI of f represents the power spectral distribution, that is PSD of input noise. And we are considering the input noise as white noise. So that's why its power spectral distribution is uniform throughout the frequency. Here this is our SNI of f and its magnitude is uniform, and we are assuming it as constant and it is equal to n naught by 2, which is independent of frequency. So that's why you can replace SNI of f as n naught by 2. So that is integral minus infinite to plus infinite x of f square divided by n naught by 2 into df. And it also makes, let us, you have in the denominator you have n naught by 2. So I can write it as 2 by n naught, because it is independent of integration. We have taken outside the integration. So 2 by n naught integral minus infinite to plus infinite x of f square df, where x of f square is nothing but the square of magnitude of the input signal in frequency domain. But from Parseval's theorem, integral minus infinite to plus infinite x of f square df can be also written as integral minus infinite to plus infinite x of t square dt. Here you remember that Parseval's theorem states that integration of square of a particular signal in frequency domain and time domain are equal. And that's why we are, and also we are considering the bit interval as TB. So that's why you can write the square of output SNR rho max as 2 by n naught integral 0 to TB x of f square df. That can also be written as 2 by n naught integral 0 to TB x of t square dt, where x of t is a change in the input signal, which is equal to x1 of t minus x2 of t, where x1 of t is the positive magnitude of the input and x2 of t is the negative magnitude of the input. And rho max can be written now as 2 by n naught integral 0 to TB x1 of t minus x2 of t square dt. Now let us substitute x1 of t for PSK as root 2 ps cos omega ct and x2 of t as minus root 2 ps cos omega ct. So because we know the positive magnitude as well as negative magnitude of binary PSK. We already studied it in the earlier module. That is in binary PSK module, we completed this, and we know the positive magnitude of input as root 2 ps cos omega ct for data bit 1. And this root 2 ps is nothing but the amplitude of carrier, which we have written in terms of power dissipation. And similarly, negative magnitude is minus root 2 ps cos omega ct for data bit 0. Let us substitute the positive and negative magnitudes of BPSK signal in the square of output SNR. So you will have 2 by n naught integral 0 to TB root 2 ps cos omega ct minus of minus. So it will be plus root 2 ps cos omega ct whole square. So you will have same root 2 ps cos omega ct plus root 2 ps cos omega ct, that is 2 into root 2ps cos omega ct whole square. And now we can write it as rho max is equal to 2 by n naught integral 0 to tb 2 into root 2ps cos omega ct whole square dt. Where please remember that 2 square. So please see here, let us go through the simplification. So 2 into root 2 ps whole square, so that will be 8 ps, 8 ps into 2, so 16 ps by n naught integral 0 to tb cos square omega ct, where cos square omega ct can be written as 1 plus cos 2 omega ct whole divided by 2. Here you have two terms, and out of these two terms, once it is allowed to the low pass filter in the output receiver, low pass filter does not allow the high frequency component. This is the second harmonic of carrier. So rho max will be only 8 ps by n naught integral 0 to tb 1 into dt. So that is um, t within a limits 0 to tb. Upon applying the limits, you will get it as tb. So 8 ps into tb divided by n naught. So output SNR can be obtained by taking the square root of rho max. So output SNR is equal to root rho max, which is equal to x01 of t minus x02 of t by sigma. So just apply the root of rho max. This is nothing but our output SNR. So we have taken root 8 EB by N naught as output SNR. And if you see this, the output SNR for BPSK system is almost all double to that of BASK. Because for BASK you obtain like almost all half to that of BPSK. Now let us move to the calculation of output SNR. And we obtained it as root 8 EB by N naught. Just to substitute the output SNR in the expression of probability of error. So half ERFC of x01 of t minus x02 of t by sigma, 2 root 2 sigma. This factor is nothing but our output SNR, which is root 8 EB by N naught. If you take this 2 root 2 inside the root, it will be 8. So root of 8 EB by 8 N naught. So 8 gets cancelled. So you will get half ERFC of root EB by N naught as the probability of error for BPSK. So if you want to compare the probability of error for BPSK and BASK, in BASK we obtained the probability of error as root EB by 4 N naught. But here it is root EB by N naught. So we can say that the probability of error is reduced to half over BASK. So because the probability of error is reduced, obviously the SNR for BPSK system is better when compared to ASK. So in this module, we calculated the output SNR and probability of error for BPSK. We obtained output SNR as root 8 EB by N naught and probability of error as half ERFC of root EB by N naught. So let us continue with the probability of error calculation for FSK in the next module. Thank you for listening.